let me quickly review what I was trying to say. In a continuum approximation is a fluid particle. Fluid particle is not a molecule, and then it is assumed to be a point mass. Entire fluid is assumed to be a continuous distribution of point masses like this. Every fluid particle has a velocity. Let's denote it by Vpi, where P is one particular fluid particle with respect to a frame. Let that frame be I, like here. Every fluid particle has an associated density, kg per meter cube. Every fluid particle has temperature and pressure associated with itself. Let's denote them by Tp and Pp. So big P means particle, that particular particle P. Units will be Kelvin, Newton per meter square. Every fluid particle has a fixed mass by definition, does not change with time. So in continuum paradigm, it is assumed that a fluid particle has no dimension, it has point mass. However, in reality, a fluid particle has dimension. How much is the dimension? It is of this order. On absolute scale, a fluid particle can be visualized as a cuboid of dimension this much at a reference time. So you start observing a fluid particle at, say, T ref, right? T ref, T reference. At that time, you can visualize the fluid particle to be a cuboid of this dimension. Continuum sees that as 0, 0, 0. On absolute scale, it's not 0. Also, I want to remind you, this is the dimension of a probe. 2 classes ago, I was talking about a probe with which you measure velocity of a fluid particle, pressure, temperature. That probe will have dimensions 0.1 millimeter, 0.1 millimeter cross section area. That is considered to be the dimension of a fluid particle. With time, this cuboid may deform. Indeed, it may change its shape, may change even its volume. But the mass associated with that will remain the same by definition of a fluid particle. The volume may change, but it will not become very large. It will still be of the order of magnitude this much. It still remains very small. So continuum is fine taking that to be almost 0 in its own paradigm. So molecular description is looking at the fluid as a collection of molecules. Continuum description is looking at the fluid as a collection of fluid particles. On the other day, I was giving this example of molecular velocity in this room. We have an understanding it is about 300 meters per second. If I take put a table fan here and switch it on, you will feel a breeze of air. And if I ask you what is the velocity of that, your estimate will be 2, 3, 4 meters per second. So there are 2 types of velocities that we are talking about. One is the velocity of molecules, the other is the velocity of the breeze. That breeze velocity, what you sense as a human being, what we sense is the velocity of a fluid particle. All right. So there are 2 types of velocities occurring at the same place. There has to be some kind of relationship between the 2. Molecular velocity on one hand and fluid particle velocity on the other. I call that as the handshake relationship, handshake equations. On one side, the molecular description comes, and the other side, continuum description comes. They must shake hands. There must be a relationship between the quantities. Here is the relationship. Here is the list of relationship. So in this volumes of fluid particle, at a given instant, say there are n number of molecules residing inside it. Okay, and that number is going to be large. It's going to be of order 10 to the power 10 or something around that. Very large number. the velocity of this fluid particle with respect to this I frame is on my left hand side, and this is the handshake equation. On the right hand side, I have summation of mi vi I divided by summation of mi. What is this mi? Mass of the ith molecule in that box. What is VII? It is the velocity of the ith molecule with respect to I. Does this relationship look familiar to you? What is this relationship? Center of mass. If I give you a bunch of n particles, molecules or whatever, and I ask you to find the center of mass velocity of that system of particles, you will write it like this. Indeed, that is VPI. So even though in this box, the molecules themselves are moving around 300 meters per second with respect to ground frame, when you average this like this, in this manner, that velocity turns out to be what? If there is a table fan in this room, around 2-3 meters per second. Is it possible? Algebraically, is it possible? It is possible. Why? Because molecules tend to move in random direction, and that's why they tend to cancel out lot of velocity quantum, and what is left is the breeze velocity VPI. Of course, if this room, in this room, the air is stagnant, if I use this word stagnant, what I actually mean is, if I say the air in this room is stagnant, I'm talking about continuum description. And in that case, what is this? Zero. And yet the molecules are having it all sorts of momentum. Okay, that is the handshake relationship. Density, again a continuum quantity, has no significance if you start seeing molecules in life. Continuum coming from left hand side and see what is on the right hand side. Does it make sense? I have explained the symbols already. Does it make sense? Numerator is the total mass of the molecules currently residing in that box divided by volume of fluid particle, whatever it is, 10 to the power minus 12 meter cube. It will turn out to be the density. Temperature, down there at the level of molecules, there is nothing like temperature. Temperature is human perception. Of course, you can have a mathematical interpretation to it, but as a civilization, as a species, we first perceived it, and then we found out how it is related to molecular motion. So what we perceive as human beings as temperature is proportional to what I have on the right hand side. I have just written proportional to. There are more details. I don't want to explain. I don't have time to explain all that, but at least I want to bring in the velocities, the two velocities I talked about. Look at this relationship, proportional. What I have on the right hand side, of course, mass of individual molecules, and then VII minus VPI. So I'm talking about velocity of the ith molecule relative to the velocity of the fluid particle itself and with respect to frame I. In APL 100, I used to say these long sentences once in a while, at least half of you who were with me. Velocity of particle P relative to particle Q and with respect to frame I. That's the kind of thing you have there. So in a way, you can say that the temperature is a measure of kinetic energy of the molecules, where that kinetic energy is being computed using the velocity of the ith molecule over and above the velocity of the fluid particle itself. See that? That's what temperature is. Okay. And of course, there is some n and mi, n is there, and is the same number of molecules there. So the translational kinetic energy of molecules, somehow we have felt that as temperature and started calling it temperature a long time ago as we evolved as a species. Pressure. Again, I'm not giving the full expression, is proportional to the same thing with some other factors. At one point in this course, I will give you more insight about what pressure is. When I talk about fluid stress, more information I'll give. For the time being, I think it is adequate for us to understand these relationships, the handshake relationships. All right. Now, committing to continuum, we will forget or would like to forget everything that is on the right hand side, would like to focus on only on the left hand side. This is our desire, not to worry about this. But you will realize later that when you talk about fluid stress, these things will come back to you. Somehow you will have to account for that. We will see that later. Yeah, for some peculiar reason, this velocity is called peculiar velocity of the ith molecule. Just a piece of information. Okay. So we are committing to continuum description, and let's now talk about two types of description, Eulerian and Lagrangian. I would describe both of them, and then I would tell you the advantages and disadvantages of both of them, and we will make a choice. We will choose one of them, and I will try to explain why we will choose one of these as we move ahead. This is the preferred choice for us. We will understand the reasons. Okay. Let's start with Lagrangian. Before that, few definitions I want to mention. A field and a process. I'll use this word quite often now onwards, so I thought I should first explain what I mean by that. Strictly speaking, mathematically, a field is a function which depends on space. If I'm working with Cartesian coordinate system, x1, x2, x3 are the Cartesian coordinates. I have a function like this, dependent variable, depends on these independent variables. A function of space is called a field. We will say f is a field, or I would say f field. This kind of language I will use, the f field. So when I say the f field, mathematically this is what it means, depends on x. A process, mathematical definition is this. There is a function which depends on time. When it depends on temporal variable, we call it a process. Okay. You can have situations, indeed, we will have that kind of situation all the time in fluid mechanics, where you have a variable, dependent variable, that depends not only on space but also time, like velocity. In general, if there is a flow in this room, the velocity will depend on x as well as it depends on time. With time it will evolve. If you come 1 hour later, the flow field may be different. In that case, strictly speaking, we should say that h is a field at a fixed time. Does it make sense? F is a field, h is a field at a fixed time. So at a fixed time, if you look at h, it depends on x, so it's a field. And it is a process at a fixed location. So you focus on this location, h will change with time. So it's a process at a fixed location. However, me and others often would refer to this quantity also as a field. I will not use this long sentence. It is a field at a fixed time, process at a fixed location. Strictly speaking, we should use, but we will not use. I will just take the liberty to use the word field even for this situation. This is just a matter of convenience, but I'm telling you so that it is clear when I communicate. I will also use this phrase quite often, a flow field. Okay? A domain in which fluid is flowing, I will refer to as a flow field. And flow field will be the set of many h, like velocity field, density field, temperature, and pressure. So when I say a flow field, I actually mean this set of velocity, density, temperature, and pressure field prevailing, existing in a flow domain like this. All right, that would be the meaning. Lagrangian and Eulerian. So when we talk about Lagrangian description of fluid motion or the Eulerian description of fluid motion, keep in mind that the difference in these descriptions are simply because of the choice of independent and dependent variables. Here I will choose some independent variable that will make it Eulerian Lagrangian. If I change the way I choose my independent variables, it will become Eulerian description. What those differences will be, I'll talk in a little while. But keep this in mind that this adjective is about description. It is not an adjective that describes a reference frame. Many textbooks actually use this adjective wrongly with reference frame. They mean exactly what I am going to tell you, but they just use this adjective in a wrong way. This is not an adjective for a reference frame. Indeed, what will happen that if you are talking about two descriptions, the reference frame will be the same. The object, solid object around which you are monitoring the flow field remains the same. The flow itself remains the same. I mean, it's the same bunch of fluid particles. Alpha, beta, gamma, Peter, John, whatever fluid particles are there, they are the same. And yet you can have two descriptions. Is this idea clear? Clear? It's a very confusing thing when you read other textbooks. So I want to make it very clear. Now, what makes my description Lagrangian? Independent variables are t and y. If I choose t is time, current time instant. Whenever I say t, it means current time instant, right now. And the other independent variable is actually a vector. So if you use a Cartesian coordinate system, it will have 3 coordinates, right? But for the time being, I am treating this as full vector, 3 scalar components inside it. What is y? Y is the position vector, acronym PV, of an arbitrary fluid particle at t ref. So when you start describing a fluid motion, you will take a reference time or the beginning time or when you started observing the motion. Without loss of any generality, I will take t ref to be 0. Unless specified otherwise, my t ref will be 0. So at t0, you start observing the flow field. All right. At that time instant, at t0, you identified a fluid particle. Let's call it particle P. It will have a position vector measured from where? Measured from the reference frame F and an origin. You understand origin of a reference frame? Origin of a reference frame is just a point on the reference frame which is fixed to it. All right. What is the utility of origin? You measure position vectors. KPL 100. So this is where the fluid particle was lying at T0. That is what Y is. That I take as an independent variable. It is just a mathematical way, if you think about it, it is a mathematical way of naming a fluid particle. Think about it, what I'm saying. If we are very creative and we can come up with a million nice names for fluid particles, Peter, John, David, Ram, Shyam, then I would not need this kind of naming. I would actually name them, my favorite names. And then I would say at T0, Peter was at Connaught Place. I want to know at this time instant where Peter is. Will that question be of pertinence? Could be. You want to track fluid particles. All right. So instead of calling them by creative names, this is a mathematician's prescription that you name them like this. Where it was, it would be at a unique position, so it gets a unique name. All right. So that becomes an independent variable. Now at time t, t means current time. Your favorite fluid particle is here. Peter is here. And Peter has a new position vector. New position means the current position vector. Is that a dependent variable or independent variable? In this description, it is a dependent variable. Because the independent variable is y, that has already been chosen. So this will be a dependent variable. This is the instantaneous at time t position vector of that fluid particle. Look at this sentence. Of that fluid particle which was at y at t equals 0. Now we have more somehow. I'll leave this comment. This is like, if you think about it, something else came to my mind. I'll say that later. This is actually more like APL 100. APL 100, what is the situation? I give you a particle, I say I'm putting so much force. You tell me where it will be at a later time. Is this a typical question? Could be a typical question in APL 100. Right? Is particle an independent variable there? So there are a bunch of particles. You choose a particle independently. You say I am interested in where this particle goes, say the fifth particle. So fifth particle is an independent choice. You follow what I'm saying? I give you 1000 particles in APL 100 and I say that give me the position vector of the fifth particle at 5 seconds. Is the choice of fifth particle an independent choice? It is. I could have said sixth particle or seventh particle. But once I choose the fifth particle and I am asking you to find where it is currently, is that an independent choice? Can you just come up with numbers at 2, 3, 0? You cannot. You will have to find that. It becomes dependent variable. Follow that? That's what is happening here. This is exactly like APL 100, just a fancy way to write it in terms of function. Okay. Now in Lagrangian description, we put a plus here. You might be wondering why I have put plus here. Convention. We put it there because we want to convey as an engineer, as a scientist to the other person that I am talking about which description? Lagrangian description. To contrast it with what? What is going to come next? The Eulerian description. All right. So this is a Q. What else could be dependent variables in the flow field, in this flow field? You have chosen T and Y to be independent. What else could be dependent to describe the fluid motion? I want you to guess. I have it on the next slide. So in continuum description, what we were interested in? Handshake relationships I wrote. What were the things on the left hand side? Velocity of a fluid particle, pressure associated with that, temperature associated with all those become dependent variables like this. I will write something like V plus T comma Y, and then I will ask you to make a sentence out of it. I mean, whatever we have done, that has become powerful enough that I just write this expression and the meaning should be clear. What is the meaning of V plus T comma Y? First of all, plus means it is Lagrangian description. V means it's going to be velocity, and whenever it is velocity, it will be of a particle, rest assured. Whenever it is velocity, it is going to be of a particle with respect to a frame. APL 100. This is how velocity is defined. I am not mentioning a reference frame here, but that is default. If you have two reference frame in context, you will have to put something like here, this as well. For the time being, let's not go there. Let's understand the other things. So there is a frame, there is a particle. Now, if it is the velocity of a particle, There are two questions. At what time instant? T, current time. And then of which particle? Y itself is not a particle. Give me the full sentence. Sorry? That particle which was at Y at time t0. So much meaning is there. And that's why I would write this sentence: instantaneous velocity of that fluid particle which was at Y at t0. And then P plus Ty. Instantaneous pressure associated with that fluid particle which was at Y at t0. And then rho plus, and then T plus. Okay. If you are tracking all fluid particles using these fields, are these fields? They depend on space. They also depend on time. So ideally I should call a process and a field, but as I acknowledged earlier, I will still call them a field. So these are fields. I will call them fields: velocity field, pressure field, density field, temperature field, but in Lagrangian description. All right. So Lagrangian description, the summary is the independent variables are t and y. The moment you choose them to be like this, it becomes Lagrangian description, and then this emerges as the set of relevant dependent variables. You can have more dependent variable. Who stops us? We can talk about stress, which will come later. That will also depend on these things. So there could be more dependent variables, but at least this much we want to track. This much is fundamental. Okay. Is this idea clear? All right. If this is clear, then we will move to Lagrangian. As I mentioned earlier, this is more intuitive. Same as APL 100, but yes, the expression is little bit complicated, which I hope I have explained by now. Before I go to Eulerian, I want to bring to your notice this relationship. I have written a relationship, this Lagrangian description. Does it make sense to you? Please see. In the light of APL 100. Does it make sense? Is this correct? So what is the context? Let me first explain this. Reference frame. I have a reference frame of fluid particle which at time 0 was at Y. And then after some time has elapsed, 15 minutes have elapsed, this particle is found to be here. And the position vector is being denoted by this. And in between it did fancy things. It moved according to its mind. It followed a trajectory. I want to know this. Is this correct? Or not correct? Have I written it incorrectly? What will this give me? I hope I have written correctly. I'm not getting any response. What will this give me? Or what will this give me? Forget the integration. What will this give me? Velocity of a particle multiplied by small time increment. What does that give? Displacement. So if the particle was at this location, this is the position vector, it underwent this much displacement. I add this displacement to this, what do I get? The new position vector, right? Right? That's for small time increment. But if it is for a long time, what will you do? You will integrate. Am I right? That's what it is. That's what it is. Does it make sense? Okay. Keep this in mind. Example of a Lagrangian velocity field. So suppose my working coordinate system is a frame embedded Cartesian coordinate system, something like this. Frame embedded Cartesian coordinate system. Then y, like any other position vector, will be written in terms of its scalar components like this. And then possibly the velocity field of the whole flow field or the velocity of the entire flow domain can be written first in a functional form in this way: t y1 y2 y3, and it could be something like this. This is just a random example I am giving you: a y1 e1, b y2 square e2, c y3 y2 e3, where a b c may be depend function of time. Okay. So which particle you are talking about that is controlled by y1, y2, y3, and it has a dependence on what velocity this particle will achieve at a later time. Also, time has a role to play. An example of Lagrangian velocity field. How do we get this? I have just created an example randomly, but in flow fields of practical application in which you are interested, how do you get this? That is the reason we are taking this course. How to predict that the velocity field be of that type or something else. That is why we are taking this course. We will need the governing equation one day in this course, and on one day we should be able to solve that equation. Does it make sense what I'm saying? All right, so how we get this is not important, but understand what I'm trying to express by trying to convey by showing that to be a possible function of y1, y2, y3 and time. Let's come to Eulerian description. Same frame, emphasizing same frame, same origin, same flow. Flow doesn't care whether your frame is here or there. Flow doesn't care whether your description is Eulerian or Lagrangian. This is all our choice to track the flow field. Independent variables t, x. T is time. What is x? X is the position vector of an arbitrary location. How is it different from the previous choice? How t, x, where x means this, is different from t, y, where y meant what I said earlier. Both are spatial coordinates or both are position vectors. Say it louder. Chosen particle की, और यहाँ x क्या है? Arbitrary है. मैंने उंगली रख दी यहाँ. t टाइम तो टाइम है इंडिपेंडेंट, और किस लोकेशन पे मुझे वेलोसिटी फील्ड चाहिए, दैट आई एम नॉट केयरिंग हु इज लाइंग हियर, वेदर इट इज पीटर, जॉन, राम, श्याम, आई डोंट केयर. दिस इज माय चोजन पॉइंट. आप मुझे बताओ यहाँ वेलोसिटी क्या है, यहाँ टेम्परेचर क्या है, यहाँ प्रेशर क्या है. That is an independent choice of location. Once you do that, that's what is called the Eulerian description. Okay, and in Eulerian description, the dependent variables will be v. In fact, the variables themselves, the identity of variables themselves will be the same: velocity, pressure, density, temperature. But now they will be function of time and x, where x is chosen by whom? Me, you, the probe, the person who is probing the flow field. You see the difference, Eulerian, Lagrangian? Okay. Vxt, again, this symbolic notation should now be powerful enough to be felt by you and to be able to convince yourself that this would mean instantaneous velocity, again, of a particle with respect to a frame. Frame to wahi hai. Which particle? That fluid particle which is abhi currently occupying location x. That's what it is supposed to be. Okay. I don't care, again I'm repeating, I don't care which particle is there, but there is one particle, that is for sure. As long as you are in the flow domain, there will be a particle. Koi bhi hai, coincidental, the identity of the particle is coincidental. जो भी है उसकी velocity बताओ, vxt. और फिर pressure or density or temperature, instantaneous pressure associated with that fluid particle which is currently at location X. Fine. This is the summary. Eulerian description the description will become Eulerian the moment you choose X and T as the independent variable, and dependent variable will be V, rho, T and P. पिछले वाले सेट में 5 चीजें थी. So let's go back. Velocity, pressure, density, temperature और X plus V था dependent. Current position vector was a dependent variable in Lagrangian. Here it is not. What is the current location of this fluid particle? What is the current location of the fluid particle we are talking about here? X. और वो तो independent है. There is no need to calculate that. वो तो आपने choose किया है. ठीक है? All right. Now, as far as the notation is concerned, I talked about one Q, but actually there are two Qs. Two Qs, two hints that engineers and scientists try to convey. When we talk about Eulerian description, phi is any placeholder, a placeholder for velocity, temperature, pressure and all. One Q is plus, Q1, Lagrangian you will put plus, Eulerian you will not put, no plus. That's Q number 1. We are adding redundancy. The second hint is, in Lagrangian description, by convention, first the temporal independent variable is written, and then the spatial independent variable is written. यहाँ क्या हो रहा है? उल्टा कर दिया. You will follow this practice. You must follow this practice. On an exam, if you don't follow this practice, I will have no choice but to interpret it the other way. If you don't put plus, I will interpret it as Eulerian. But then you can say that I had a redundancy. I did not put plus, but I put this order. There is a redundancy, but I will still not give you marks. I want you to follow both the Qs. Okay, only when both the Qs are there, then I will read that as the Lagrangian field of pressure, temperature, density, whatever it is. Example of an Eulerian velocity field, just made up an example. It could be something like this, with Cartesian coordinates being your working coordinate system. It could be something like this. It may have dependence on x1, it may have dependence on x2, it may have dependence on x3, and then time may appear explicitly. AT I have written, and A, B, C, D, other things may be constants. This is an Eulerian velocity field. Okay. In problem set 2, I'll give you some practice problems on these two things, Eulerian and Lagrangian. You get a better insight, I am sure. Now, having understood these two types of description, I want to raise a question which will be of lot of importance when you start applying governing laws of motion to fluid particles. Governing laws like what? Newton's second law. If you take a system, if you take a particle, Lagrangian choice, Lagrangian description. If you take a particle, if you put F is equals m times A, right? That kind of law, if you think about it, is applicable only to an identified fluid particle. All right. So whether it is Lagrangian or Eulerian, you will have to find rate of change of velocity of a fluid particle. That will give you acceleration. So let me raise this question. Let us write the mathematical expression of the current. Current means instantaneous, time t. Current rate of change in temperature following that fluid particle which was at y at t0. Long sentence. Every word is meaningful though. Rate of change in temperature following that fluid particle which was at y at t0, and that rate of change to be found at this time instant, not at any time in the past. In Lagrangian description, my claim is that what I am writing as a long sentence in the language of calculus, that's what it means. Please pay attention to that expression. I have taken two measurements. पहली बात तो है जब भी rate of change आप calculate करो दो measurements करने पड़ेंगे. You agree with me? Rate of change. Two measurements are required. Obvious. So I have made two measurements. First measurement is what I call as the base location. Now location in generally means in space, but I have added temporal aspect also to it. So at a current instant, at this particular spatial location, I call that as base location. So I am interested in finding rate of change of at this time instant of the fluid particle which was at this at time 0. ठीक है. So base location पे एक measurement ले लिया. अभी temperature 5 Kelvin है उसका. I want to find rate of change. I need to make one more measurement. Now the next measurement that I am going to make, what I will have to do? I will have to follow that fluid particle. Mind you, it is a flow, so that fluid particle will keep moving. So at the next time instant, that will go somewhere else. And you have to make the second measurement again there, wherever it goes. But in Lagrangian description, wherever it goes, it is really not troubling me right now. All I have to do is to ensure that both are y, same fluid particle. So mathematically, this is what will be the change divided by delta t. That should give me what I am writing in this long sentence. And the moment I finish writing it, I realize indeed the exact symbol of this mathematical expression is this. Partial with time. Partial with time means what? Only change is allowed only in time. Other independent variables are kept on mute. They are not allowed to change. That's exactly what is there. So this is coming from the sentence. That English sentence is giving me this expression. And once I get this expression, I realize I can use this symbol of partial derivatives. Okay? Very simple expression for Lagrangian. Now, if I change my question, what is the expression of the instantaneous acceleration of that fluid particle which was at y at t0? Acceleration I know is rate of change of velocity of that fluid particle which was at y at t0. I am interested in current acceleration. I am going to write this, translate this English sentence into this first. Two measurements on velocity, one at the base location, one at the next time instant, wherever the particle is going, but I am making the measurement on the same fluid particle. I know that for sure because I am keeping this as y. And once I have written this, I realize that also can be written as partial derivative with time itself. Similarly, I ask you any other quantity, rate of change of pressure associated with that fluid particle which was at y at t0. You will be able to write that, provided you have this expression. But mathematically, this is the representation. So that looked quite straightforward in Lagrangian description. Now come to Eulerian description, and I raise another question. Mind you, this is not exactly the same question that I raised earlier, but it is a similar question. Please read that sentence, English sentence in there. Instantaneous rate in temperature associated with that fluid particle which is currently at x in Eulerian description. Not exactly the same, but similar. Similar क्यों है? क्योंकि rate of change of temperature associated with a fluid particle मैं पूछ रहा हूँ. पिछली बार भी यही पूछा था. Same क्यों नहीं है? क्योंकि last time मैं कह रहा था of that fluid particle which was at y. अभी मैंने compromise सा कर लिया. Apparently looks like a compromise. Whichever fluid particle is there at x, give me the rate of change. In that way, it is similar but not the same. ठीक है? These questions are of significance, as I mentioned earlier when we derived governing equation. In Eulerian description, this will be of significance, and that's why I'm raising it. Now let's look at the mathematical expression of it, how we will get that. First of all, the plus is gone. Why? Because I am dealing with Eulerian description. Also, the notation x, t, tx wali cheez, I have made sure that it is, we are following. The question is this the answer to this question? Yes or no? Looks very intuitive. Last time we partial derivative kiya tha. After all, I am asking only rate of change with time. Mind you, the rate of change मैंने जब कहा है वो time ही है. Maybe I should write it with respect to time. Last time it was also time. Now also it is time. So you feel like rate of change with time. Partial Lagrangian में भी partial derivative ही लगा था. Let's put it here. That is the answer of this question. That is not the answer to this question. This is incorrect. Why it is incorrect? Let me explain. Mathematically, this means what? You will not change x. If you don't change x, this is what the expression is. Limiting value tx x, t plus delta t, t divided by delta t. You have not changed x. What is the problem? Your particle has moved on. You made two observations. First observation is absolutely fine. Whichever fluid particle was there, you measured the temperature. But then whatever your probe was, suppose your probe was a kind of a remote probe. I mean, you position, it's like a gun. You position it on the fluid particle and you get the temperature back. Suppose the probe is like that. What is being done here is, first measurement at time t, x is fixed. You get a value, 5 Kelvin. And then at t plus delta t, you are not changing the orientation of the gun. You are keeping it at the same x. You are getting another measurement. Indeed, you are. But which fluid particle is there at that time? Not the fluid particle which was there at time t. That fluid particle has moved on. With what? Its local velocity vector. And it has gone somewhere else. And you are making the second measurement on a totally different fluid particle. And that is why this quantity or this quantity is not what is being asked for. Is this idea clear? Two different measurements. Just half minute I'll take and let you go after that. So how do we correct this situation? Maybe it's a lot, I won't be able to talk, but how do we correct this situation? To correct this situation, the second measurement has to be made at a new location. And how will you know that location? Local velocity time delta t. Okay, so what you will get is the quantity that we are asking in an English sentence will be something like this. You look at this. Time has changed, t to t plus delta t, which is obvious. X has also changed. This was x, this has become x prime. And what is the relationship between x prime and x? All right, we will use this, apply Taylor series approximation. Have you studied Taylor series approximation? We will do that, and then we will see what expression we get in the next class. We stop here now.